Good morning everyone. So today I am here with the part 4 of the same chapter, real number, of class 10. So let's get started. So we are completed with theorem 1.1 and 1.2. 1.1 was Euclid division lemma, 1.2 was fundamental arithmetic, and 1.3 we are going to start now. So what is 1.3? Let's see. Let P be any prime number. If P divides A square, then P divides A, where A is positive integer. So it is saying we are taking any prime number. If it is divided by A square, then it should also be divided by A, where A is a positive integer. So let's understand this theorem with the example. So here is our example. I have taken a prime number, that is 2. It is divisible by 10 square, then it should be also divisible by 10. It is a theorem that is saying that P is any prime number. P is divisible by A square, then it should also be divisible by A. Here I have taken 2. It is divisible by 10 square, then it should be divisible by 10 also. Right? Understood? Okay. You have to learn this very carefully as it is going to help in the next theorem also. Okay, read this carefully. Now we will do theorem 1.4, that is root 2 is irrational. After proving this, we can also conclude that root 3, root 5, root of anything is irrational if it doesn't have any root of it. Like root 4 is irrational because it is 2. Okay, so we have to prove root 2 is irrational. So let's see how to do so. We all know that root 2 is irrational, but how to prove it? We are going to do now. Okay, so we know it is irrational, but we have to prove it wrong that it is rational. Right? So let us assume to the contrary that root 2 is rational. If we prove that root 2 is not rational, then of course it will be irrational. We are going to do the same. But you have to start with let us assume to the contrary that root 2 is rational. This statement is very important. Okay? We have assumed that root 2 is rational. So root 2 can be written as in P by Q form because every rational number can be written as P by Q form where Q is not equal to 0. And in bracket you have to write that P and Q are co-prime. Now, what are co-prime? We have understood this in the previous classes, but still for revision I am telling you what are co-prime. So co-prime are the two numbers that don't have any common factor except 1. Like we have taken P and Q as co-prime. So if I am taking two numbers at 2 by 3, so 2 and 3 do not have any common factor except 1. Right? So these are co-prime number. More example are 4 by 5, 8 by 9, 5 by 2. They do not have any common factor except 1. Understood? We have understood what are co-prime. So root 2 is equal to P by Q. We can write because root 2 is rational. We have assumed that and P and Q are co-prime. So I can take the Q that is in divide will multiply and in that side. So I can write Q root 2 is equal to P. Now we have to square both the side. Q root 2 ka square is equal to P square. Okay. Now we will square both the sides. So Q root 2 square is equal to P square. That I will get Q square into root 2 square is equal to P square. Or 2Q square is equal to P square. I have got it. Okay. Now theorem 1.3 comes. According to theorem 1.3, I can say that 2 divides P square. Why? Because if I will take 2 that is in multiply with Q square can come in divide with P square. Right? So 2 divides P square. And if 2 divides P square, then it should also divide P. Right? According to theorem 1.3. So I can say that 2 divides P. Right? Now as I said that 2 divides P according to theorem 1.3. So P by 2 let's say is equal to R. Okay. So I can write P is equal to 2R. I have taken any number R. Okay. This can be any natural number. So P is equal to 2R. So I will place 2R instead of P now. Okay. Now here I have taken P as 2R. So पहली इक्वेशन क्या थी 2Q square is equal to P square. Now I will replace P with 2R. So 2Q square is equal to 2R whole square. I will get 2Q square is equal to 4R square. Now 2 will cancel with 4. So I will get Q square is equal to 2R square. Right? Now again, according to theorem 1.3, 2 divides q square. Why? Because I can take 2 in divide before the equal sign. So 2 divide q square. If 2 is dividing q square, then it should also divide q, according to theorem 1.3. Understood? Now what can I conclude? That 2 divides p as well as q. So p and q cannot be co-prime. Why they cannot be co-prime? Because co-prime have no common factor instead of 1. But they do have common factor, that is 2. So they cannot be co-prime. So it means that thing we have assumed goes wrong. This type of question comes in exam. Okay, so in start you have to write, let us assume to the contrary root 2 is rational, right? But this contradiction, our assumption goes wrong. So in last what you have to write, this contradiction has arisen because our incorrect assumption that root 2 is rational. So root 2 is irrational. What does it mean? If root 2 is not rational, that is irrational, and we are complete. Similarly, now I am having one more question, that is 3 plus 2 root 5 is irrational. I have to prove this. How to prove this irrational? Let's see. So again, let us assume to the contrary 3 plus 2 root 5 is rational. So I can write 3 plus 2 root 5 is equal to p by q form, because rational number can be written as p by q form where p and q are co-prime, right? So what I have done here is I have taken root 5 and p by q, and the 3 that was positive in that side I had taken as negative this side, and 2 that was multiply I had taken as divide. So I have just rest with root 5. Root 5 is equal to p by q minus 3 by 2, and if I will take the LCM, I will get root 5 is equal to 2p minus 6 upon 2q. Okay. Here I have taken root 5 is equal to 2p minus 6 upon 2q. So here I can say that 2 minus 6, p and q are some integer. They all are integers. So 2p minus 6 upon 2q is rational. Okay, because these all are integers. So root 5 is also in equal, right? So I can also say that root 5 is rational, right? So let's see what we do have to do next. Okay, we have proved that root 5 is rational, but according to theorem 1.4, root 2 is irrational. Similarly, we can prove that root 5 is irrational, right? So we can say that our assumption was incorrect. This contradiction has arisen because of our incorrect assumption that 3 plus 2 root 5 is rational. So it is not rational. It means that 3 plus 2 root 5 is irrational. Hence, proved. Okay. Now we are completed with exercise 1.3.